Okay, good day. This is AP Calculus. I am Mr. McCulley. This is the presentation on section 3.1, Extrema on an interval. We want to get to it. So here we go. Today we're going to talk about finding extrema of a function on an interval. And we're going to find the relative extrema of a function on an open or closed interval. So before I get too far into this, I want to talk about what this chapter is going to pertain to. This chapter is going to pertain to applications of the derivative. And a couple of the things that we're going to talk about with a derivative is finding extrema. And extrema are going to be maximum and minimum points. And so when we start talking about optimizing a function, what is the best value that I can use to get the most out of this? Or what is the value that will cause the function to be the smallest, to be the most efficient? These are extrema points, and they can either be on an open or closed interval. And so we want to talk about what those things really are. And extrema are extreme points, either high or low relative to the points that are arbitrarily close to the extrema. Now, there's that word arbitrarily close. What does it mean to be arbitrarily close? And again, the best example or the best definition that I can give to you is close enough to that point. And so in pre-calculus, we use technology to find these points. And we either call them relative maximum or relative minimum, or absolute maximum and absolute minimum. Now, these definitions are in the book on page 165, and I'm just going to give you a real brief overview of what those things are. Now, if I have a function that looks, let's say it looks something like this, all right, and I put arrows on the end. Now, this function has no absolute minimum or maximum because this arrow here says that it's going to continue to go on forever. So there is no absolute and down here, because it goes down forever, there is no absolute minimum. Now, there is though a point that in this general vicinity on the x-axis, this point right here is the biggest in that general vicinity. Now again, I picked these two little open parts from my interval arbitrarily. And so arbitrarily close to this point, it is the highest point. We call that a relative maximum. And this point right here, to the points arbitrarily close to it on that interval, that open interval that I just set up there, this is a relative minimum, whereas this was a relative maximum. All right, now here's the thing. If this is, well, excuse me, I should say the interval for this function is all real numbers, but if that interval is closed or something smaller, we could have something completely different. So, as a for instance, if I were to draw a function that looks like, say, this, right here, this function f of x on this closed interval, and I really don't want to have any numbers on this, so I'll just turn that off for right now, I guess. And let's move this back up. Okay. And so this particular function here, this point here is still a relative max. Because while it is the maximum of the points arbitrarily close to that over this smaller interval, this point right here is the absolute maximum, because there are no other points that are higher on the y-axis than this one. This thing here is not an absolute minimum, and it's not an extrema, because it isn't going to give us a derivative that is equal to 0. But This one right here is an absolute minimum. It is both an extrema and an absolute minimum. All right. So moving on. A critical number. A critical number is a value for x where the derivative of the function is either 0 or undefined. And there are certainly some results for finding critical numbers. All right, so we'll find the first derivative, and anywhere where that first derivative is 0 or undefined, we are going to call that a critical number. So the results of finding critical numbers, this is where extrema may be located. These are places where the function can change from increasing to decreasing. It is a place where a horizontal tangent line can exist, and it's a place where functions are optimized, finding either maximums or minimums. All right. So there are some guidelines for finding extrema on a closed interval. A closed interval is defined like this with the brackets. This is our interval notation, closed, which means it includes A and B. This is an open interval, just again as review, where it's all of the values between A and B, but not A and B. All right, so find the critical numbers on the closed interval from A to B. We are going to find the critical numbers, or so we've found critical numbers. So we're find the critical numbers on the interval from A to B. So we're going to find all the places where the first derivative is either undefined or 0. We're going to evaluate each of those critical numbers, and then we're also going to evaluate the endpoints of this thing. So the least values found in 2 and this would be and 3 is the minimum, and the greatest value is the maximum. Now, if you get a chance, I would suggest that you, for this section, this is section 3.1, look at the graphs in problems 1 through 6 and 57 through 60 very carefully, because it just certainly gives you a picture idea that sheds a lot of light on this concept. So let's do a couple here. My first example, it says find the absolute extrema on the function of the closed interval. So I'm looking at this interval, or this function right here. It is on -2 to +2. So I don't have my graphing calculator here with me, but I do know a few things about this function here without actually having to graph it. I do know that because the degree of the numerator is greater than the degree of the denominator, it has a horizontal asymptote at y equal to 0. This is x and this is y. I also know that it has a 0 at 0, and it is the only value for x that makes it 0. All right, and so it will never be undefined because this number is always 0 or bigger. Whenever you square a negative number, it's positive. Whenever you square a positive number, it's positive. Whenever you square 0, it's still 0. So I only have a positive number here, +1. So the smallest that this bottom can be is +1. So on the negative side of the x-axis, all of these functions, I'll have a negative divided by a positive, which is a negative. So it's going to end up looking something like this. Then when I'm on the positive side of the x-axis, I'm going to get a positive over a positive. But again, I still have the horizontal asymptote at y equal to 0. So I'm going to get something that looks like this. Now, here's the thing. This particular function only goes from -2 to +2. So I really don't even care about any of this stuff over here, just to these 2 points with these endpoints right here and this endpoint right there. So the first thing I want to do, following the list that I gave in the last sheet, I want to find the first derivative of this. So I'm going to go f prime of x is equal to, now this is a quotient and there's nothing I can do to reduce it because it is a function in terms of x on the numerator and a function with terms of x in the denominator. So Hody high, so x squared plus 1 times, I got ahead of myself. So this is my ho. The high would just be 2 minus high 2x times the d-ho, the derivative of the bottom, which would be 2x, all over ho-ho. That'll give me x squared plus 1 quantity squared. All right, let's simplify. this thing will become, let's see here, I'll have 2x squared plus 2 minus 4x squared all over x squared plus 1 quantity squared. And again, I have got common terms here, so let's simplify. And when I go 2x squared minus 4x, I'll have negative 2x squared, and I'll have the 2. So I'm going to factor out that 2, and it'll be 1 minus x squared all over x squared plus 1 squared. Now, I could multiply this out, but it isn't going to make a big difference in the final answer because this thing is always going to be positive anyway. It's never 0, so it isn't going to cause an undefined. So I have to ask myself, where, or if it's never undefined, where is it 0? And the answer to that is at x equals plus or minus 1. These are my critical numbers. So following the guidelines that I said here, what I need to do is I now need to test the endpoints and I need to test the critical numbers. So since I'm trying to find points on the curve, I must enter them back into the original. So I need to find f of negative 2. I need to find f of negative 1. I need to find f of 1 and f of positive 2. So the two critical numbers and the endpoints. So when I plug in negative 2 times 2, I get negative 4. Negative 2 squared is positive 4, plus 1 is 5. This is negative 4 over 5. When I plug in 1 times 2, or excuse me, negative 1 times 2 is negative 2. Negative 1 squared is 1, plus 1 is 2. I get negative 2 over 2. That is negative 1. This next point right here, when I plug in 1 times 2 is 2. 1 squared is 1, plus 1 is 2. 2 over 2 is 1. And then 2, when I plug in 2 times 2 is 4. 2 squared is 4, plus 1 is 5. This is 4 over 5. And so I can see that this point right here and this point right here are going to be, this one's going to be 1, 1, and this one is going to be negative 1, negative 1. And so my extrema are, my absolute extrema is I'm going to have an absolute max at 1, 1 and an absolute minimum at negative 1, negative 1. All right. Next example, special cases. Now, the directions in this one say find the value of the derivative if it exists at each indicated extremum. So this thing is a special case. It is a sharp turn. And so I know f, and this is at the point. I suppose I should make sure I'm marking the correct point. It is at 0, 4. And so f prime of 0 is going to be does not exist. But we need to discuss here real quickly, and again, you're not going to see a whole lot of special cases, so you just have to have a passing understanding of what's going on here, is because when we have a regular absolute or relative extrema, what happens here is these tangent lines all tend to get closer and closer to 0. As I get closer and closer to the number, whatever x is, these tangent lines start to get to 0. On this side, these tangent lines also get closer and closer to 0 as I come to that. So the limit of the tangent lines have to be the same. And that's the reason that they're going to say that these sharp turns don't work. Now, we have the quotient function, and we're going to take the limit basically from the left hand and the right hand side and show that the limits are different, and therefore the derivative can't exist. And so the limit as x goes to 0 is going to be f of x, actually let's do it, f of x plus, shoot, real quick here, let me check my notes. Yeah, it's just f of x. That's it. So it's not the, it's the quotient. Remember, the slope is f of x2 minus f of x1 all over x2 minus x1. That is a slope function. And so I'm essentially using that. It's going to be f of x minus, well, I know that my point here is 4 over x minus x2. That's my point, 0. So f of x is going to be, as I come in from the left-hand side, so as I'm coming in from the left-hand side there, well, that function here from the left-hand side is this line right here. And so it is really the negative portion of this absolute value, which would be 4 minus negative x. And then this minus 4 here, and then it'll be over x, because x minus 0 is just x, and I really screwed that up, and I apologize. I yell at you guys for not doing this, and then I made the mistake. I have not evaluated this limit yet, so I need to make sure that I have that limit as x goes to 0. I'm sure someone is ripping at me saying, McCully, you said I couldn't do it. Why are you doing it? I haven't evaluated that limit yet. And so these two cancel out, and I get the limit as delta x, or as x goes to 0 from the left-hand side, get negative x over x. And this thing is just, I can cancel these two out. That'll be the limit as x goes to 0 from the left-hand side of really negative 1, which is just negative 1. Now, if I do it from the right-hand side, this function here is the positive absolute value. So if I use, again, this slope equation and say the limit as x goes to 0 now from the right-hand side as I'm coming in from here, well, that's still going to be f of x minus 4 over x minus 0. But because I'm using this line right here, it's going to be 4 minus x, the positive value of that absolute value symbol, minus 4. And I did it again. Holy cow. Macaulay. Limit. I just get so excited. All over, it's again going to be 0. And so these cancel. And I will get, oh, you guys are laughing at me, aren't you? I'm sure you are. Negative minus negative, or minus a negative. Macaulay made a mistake, but we'll fix it real quick here. That's a positive. That's a positive. That's a positive. And so I get positive 1 for that one. And really, that makes sense. I should have seen this. I should have said negative. That doesn't make sense because, again, this is a slope. Well, this line obviously has a positive slope, up 1, right 1. So I should have known better. And again, I apologize. So I would rather get it right and call myself an idiot than tell you something wrong. So this one is just going to be the limit. And this comes from the positive side. The limit as x goes to 0 from the positive side, this will be negative x over x, which again we know to be just negative 1, and that makes sense because this line has a slope of negative 1. All right, now since these two limits don't match, this derivative does not exist. Okay, looking, am I all the way to that one? I'm on the last one already. Oh, doing well. Last one here. This is number page 171, number 62, and it is an application problem. And since this whole chapter is on applications, we certainly want to talk about this stuff and doing some reasoning and understanding what these derivatives actually imply in real world situations. And don't ever let anybody say that calculus isn't applicable, because it certainly is. Now, in number 62, it says a lawn sprinkler is constructed in such a way that d theta over dt is constant, where theta ranges from 45 to 135, see the figure, and I'm going to draw it here. The distance the water travels horizontally is given by a function that I will write up there here in a moment, and where v is the speed of the water. Find dx over dt and explain why the lawn sprinkler does not water evenly. What part of the lawn receives the most water? Okay, so they give us this function. It's x equals v squared, oops, what is that? I don't know what that is. V squared sine, and then it's 2 theta all over, let's see here, make sure I get the right one, 32, and they say theta goes from 45 degrees less than or equal to theta less than or equal to 135 degrees. Now, since this is calculus, and we just, to be safe, remember that 45 degrees is pi over 4, and theta and 135 degrees is 3 pi over 4. Excuse me. All right. So this x here represents the horizontal distance of the water coming out of the sprinkler. All right, the distance the water travels. Horizontal distance, the water v is the velocity of the water. Now, we can assume that that is going to be a constant. And why can we assume that it's going to be a constant? I suppose we can't assume that it's going to be a constant, but the only way that it wouldn't be a constant is if someone stood on the nozzle and turned it up and turned it down and turned it up and turned it down and changed the pressure. And so we're just going to say that they turn on a watering hose or a sprinkler system and let it go. All right. Now, they tell us that d theta over dt is a constant. So the change in the angle of the sprinkler system is going to always be a constant. All right. And so they want us to find dx over dt. They want us to give an equation and then explain why the lawn sprinkler does not evenly water the lawn. So basically what's happening here is that when this angle is 45 degrees, all right, it shoots out that far and it goes to there. And then again, this is x. So as it increases to 135 degrees right there, oh, this, as it goes to 135 degrees, which would be right here, it's going to change in between. So we're going to have some intermediate versions, and this is the diagram that the book gives. So it's going to go all the way from 45 degrees to 135 degrees, and then it's going to go back and forth and back and forth. And so dx over dt, that represents the speed, and I'm going to call this a just so I can explain it. The speed at which point A moves on the x-axis. Now, if I had a nice animation, you would see this point scoot into here, and you would see this curve here. It would get closer to this, and then when it got to here, it'd be a straight line, and then as it moved back this way, you'd see it go there. But I don't have a nice animation. But I do want to find this thing and then use it to discuss where is it going to have the most water, where is it going to have the least water, and it certainly is not going to water evenly. So first thing I can do, since I want dx over dt, I'm just going to derive this thing. Now I have to remember v is a constant, d theta over dt is a constant, and so the only thing that's changing in this one is theta and x. And so I can consider this v squared over 32 to be a constant, which is really going to help make this a lot easier, because I want to do the derivative with respect to x, or excuse me, with respect to t, sorry about that, of x equaling to, and I'm going to go v squared over 32 sine 2 theta, because you can just think of this as like a 3. If I'm doing the derivative, what would I do the derivative if it was 3 sine 2 theta? It's just a constant. I'd leave it alone. I'm just going to leave it hang there. And so the derivative of x with respect to t is x over dt. I leave the constant alone, v squared over 32, and then the derivative of sine is going to be cosine, but because I have a chain rule here, I have to do the derivative of what's inside here, which would be, so I leave the inside alone, and now I do the derivative of that, which would be 2 d theta over dt. Okay, so I guess I could do a little bit of simplification and say d x over dt, and let's make this real neat because I'm going to have to talk about it for a second. V squared 30, actually it's just going to be 16 because I'm going to divide out that 2. That's what I'm going to do. That'll be nice. I'm going to divide this 2 and 32, and it'll be v squared over 16 cosine 2 theta, and then it'll just be times d theta over dt. Now this doesn't change, it's a constant. This doesn't change, this is a constant. So the only thing that changes is theta. Now we know something about cosine. Is we know that the value of cosine theta is always between -1 and +1 inclusive. Those are the biggest and the smallest values, and it goes up from all of those. So if, let's say, as a for instance, I let theta equal pi over 4. Well, if I let cosine theta equal pi over 4, then dx over dt is going to be v squared over 16, and then it'll be the cosine of, well, when I multiply by 2, I'll get pi over 2, d theta over dt. Now, the cosine of pi over 2 is 0, and so this thing is equal to 0. And so what happens is when theta is 45 degrees, this, for a moment, comes to rest. So this thing has no velocity, no horizontal velocity. So what that means is that when you're around A, it's going very slowly. Now, if we let theta be halfway between our, let's see, where is it? Our two values here. Say let it equal pi over 2, halfway between our two values, then dx over dt would equal v squared over 16 times the cosine, and when I multiply pi over 2 times 2, I get pi, which would be equal to, or excuse me, times d theta over dt, which would be equal to negative v squared over 16, because this is equal to 1, actually it's -1, d theta over dt. So basically, when my angle is sticking up straight up and down, this thing is moving at the fastest. It's moving at the fastest. Now I don't know what d theta over dt is, and I don't know what v squared is, but I do know that whatever it is, this particular point A is moving the fastest when it's around this point. So to answer the question, where will it get, where or what part of the grass gets, two S's, the most water? It gets the most water when theta is approximately equal to pi over 4, and theta is approximately equal to 3 pi over 4, because it, excuse me, not it, let's use a better word than it, because the water, not matter, the water is moving horizontal the slowest in this area. Therefore, it gets wetter. And when theta equals pi over 2, the ground does not as wet, because, and let's use around there, it's not exactly there, the water is moving the fastest. Well, that's my answer there, folks, and this is what I have to back it up. I know that's a long one, I know that's a lot, and that's all I got today. So today's Star Wars fun fact of the day: Boba Fett was introduced in the Star Wars Holiday Special as a cartoon character. There was a little cartoon interlude before they came on, and this holiday special included Carrie Fisher singing Life Day, or the Life Day Carol, because obviously there's no Christmas in space. And it also included Wookiees wearing clothing, and why, if you had that much hair, you would wear clothing is beyond me. But all right, folks, that's all I got. If you have any questions, you think I've made a mistake, please leave a comment. I'll see you in class. Goodbye.